Welcome to ePathshala lecture series in computer science, and this is a course in cloud computing. Today we will talk about mutual exclusion. Mutual exclusion in distributed system and therefore mutual exclusion in cloud. So, the learning objectives of today is that we will learn what is a mutual exclusion, and then we will see why mutual exclusion is required in a distributed system, and then we will move on to say how to implement mutual exclusion in a distributed environment and therefore directly applicable in cloud. What are the algorithms, and then we will see the mechanisms of mutual exclusion in cloud itself, which are the tools and technologies that are already using mutual exclusion, followed by summary. So, last class we looked at the election algorithms. So, we saw two algorithms, one bully algorithm and the other is a ring algorithm, and we looked at the election in cloud. This class we will look at mutual exclusion in distributed and cloud. So, what is mutual exclusion? To understand the concept of mutual exclusion, let us look at an example. We will follow the same example that we have taken earlier on, our IPL ticket example. The example goes like this, that we have Ram accessing a Chennai server and trying to book a ticket, and we have Neeta accessing a Mumbai server and trying to book a ticket for an IPL match, and our data server, that means all the data relevant to these IPL tickets are stored in a server in Calcutta. Here are the assumptions that the data server is only one, there are no copies of the data server, and that is residing in Calcutta. The second assumption is that the clocks of all the servers, that is Chennai server, Mumbai server as well as Calcutta server, are synchronized. We have learned a few algorithms in earlier modules for synchronizing. We can use an algorithm such as Berkeley algorithm for this synchronization, and let us also assume that both Ram and Neeta have accessed the server to book the ticket together at the same time, and there is only one ticket left in the server. So, how this mechanism will work out, let us look at that. So, who will get the ticket? Here is our Ram accessing Chennai server and trying to book the ticket, and here is Neeta accessing Mumbai server equally trying to book a ticket, and here is our Kolkata server, which is our data server. So, both Chennai server and Mumbai server has to connect to the Kolkata server to be able to book the ticket. So, they both query the Calcutta server to ask for an availability of the ticket, and the Calcutta server will reply to both saying that one ticket is available, because the query came together. So, the Kolkata server will reply to both Chennai and Mumbai server that there is only one ticket left, and obviously because both of them are trying to book the ticket, both of them will send a reply saying that update the server, I am booking the ticket. Both the servers will try to update the Kolkata server, but the Kolkata server, being unaware of the availability of only the last ticket, will reply to both and update the server. So, both of them will be told that a ticket has been booked, but the problem is that both of them will be having the same ticket. So, this is a problem that they will face because of the problem in mutual exclusion. So, the Kolkata server's data will show at the end of this whole process, it will show as having no tickets left, but the two people Ram and Neeta will be holding the same ticket, which is the last ticket. So, what happened actually? Let us look at why this has happened. This has happened because we have allowed the Chennai server as well as the Mumbai server to access the database server in Kolkata concurrently. This is called concurrent access to shared data. So, when a data is shared among different servers or different entities, if they are accessing concurrently, then they are getting updates which are not the current updates, and that is the problem. So, how do we solve this problem? How do we ensure that any one of these two entities get the ticket? That is what we can do by using mutual exclusion. So, we have to ensure that the two accesses are mutually exclusive to one another. So, what is actually mutual exclusion? It is that the data in the Kolkata server should have been accessed one at a time. Then this problem will not happen, and that is the mutual exclusion. Now, two different ways of looking at mutual exclusion. When we have only one system or even one operating system accessing both the being accessed by both the entities. So, if Ram and Nita would be sitting in the same server and the data also will be in the same server, even then a similar problem could have happened, and this is what we call a single system problem. And in another case, in the example given where the data server is in Kolkata and the clients are sitting in different parts of the geographically different parts locations, then this is called a multiple server problem, and this is a distributed system problem. So, in either case we need to protect the data from shared access, and we will see how to do it. So, this ability to allow only one of the clients or servers to access data which is shared among multiple entities is called mutual exclusion. So, how to resolve it? We simply need to protect the shared data. So, how do we protect the shared data? In operating system, you will learn that the data, this kind of data, shared data can be protected using what mechanism is called a semaphore. So, what is a semaphore? Semaphore is an atomic lock. Atomic lock means that the access to the lock will be indivisible, will be atomic. That means, when one entity is accessing the log or trying to test and put the log on the value, no other entity can access that. So, this is the concept of atomic lock, and semaphore is an atomic lock. Using semaphore, we can ensure mutual exclusion in a single system environment. So, whenever one system, one entity is trying to access the shared data, immediately first thing that we do even before the access is to put the lock, so that no other system will be allowed to access the data. So, the code where the data is being accessed in these accessing entities are called critical section. So, we identify in each of the processes what are the critical sections, and once we have identified it, we can put the atomic lock. So, this is an example of a single system semaphore solution. We have one process 1, and this is where the process 1 is accessing the shared variable, and we have process 2 where it is accessing the same shared variable d, and we put the atomic lock whenever the process 1 is trying to enter the CS, and this is what we call a CS, and as soon as the process 1 is trying to access CS, we put an atomic lock, and when the work is over, we remove the lock or unlock, and then whenever process 2 is trying to access, we put the atomic lock, and at the end of it we unlock it. Now, what will happen if both these are trying to access it together? Let us take this example where process 1 has put the lock and then process 2 is trying to execute the atomic lock, but process 2 will not succeed in putting the lock, and hence process 2 will be suspended or blocked. Till what time? Till process 1 has not completed the work and has unlocked. As soon as process 1 unlocks, the blocked process will be unblocked and its atomic lock will be allowed to be put, and then it will execute the critical section and will come out and unlock it. So, this is easy in a single environment, because the single system environment has a common memory. So, in this memory we put a variable which is called the semaphore, and this semaphore is accessed by both process 1 and process 2 with the help of the local operating system. So, can we implement a similar mechanism in a distributed environment where multiple machines and hence multiple operating systems are involved? But the problem is we need a common memory and a common operating system for implementing a semaphore like mechanism. So, how do we support our mutual exclusion in a distributed environment is what we have to see. So, here in a distributed environment, processes do not communicate using a common shared variable, they communicate using a what is called a message. So, therefore, no availability of a shared memory or a shared lock. So, processes must, and these messages are traveling through the network which is unpredictable. So, therefore, processes they are not guaranteed for the actual delivery time of a message. In a reliable environment, we can expect that the message sent will be message received, but the amount of time that is required to receive the message after it has been sent is not guaranteed or is not predictable. So, how to ensure that shared resources are used by these processes in a mutually exclusive manner? So, this is a system model that we will assume that communication is reliable. As we have already said, reliable communication ensures that a message sent is a message received, but it does not ensure that a message sent is received within a limited amount of time or a fixed amount of time. So, messages will be eventually delivered, and the other guarantee that our reliable communication will give is that the messages will be in FIFO order, which means that if I am trying to access a data and then I am trying to make changes in the data, the making change message will be received by the server only after the access message is received. So, therefore, FIFO order is maintained and guaranteed delivery is maintained, but no assurance is given for time. Now, our second assumption is that processes do not fail arbitrarily. An arbitrary failure is very hard to accept in such situations, and we will assume that our processes do not fail arbitrarily. Actually, even any failures can be incorporated in whatever mechanisms we propose, that we will see later on. And our third assumption is that there is a structured entry and exit from the critical section. So, critical section is that part of the program which is accessing the shared data, and there is a structured entry and exit. So, well known events these are. So, we know when the process is trying to enter and exit, and any action taken by a process can be done, which is like sending a message or waiting for a critical section to be entered, etc. So, what are the properties that a mutual exclusion algorithm must follow? Two properties. One is called the safety, which says that at any point in time only one process will be inside the critical section, and the second is called the liveness property, which says that in case one process wants to enter a CS, it should be allowed within a finite amount of time. It should not be very long. So, we will look at two kinds of algorithms. One is a centralized solution where we will use a master or a leader for communication and for executing the mutual exclusion, and the other one is called a token based solution. So, in a centralized solution, we will elect a master. We have already looked at election algorithms, and any one of these algorithms can be taken as to select a master or elect a master, and this master will maintain a couple of things. One of it is a queue in which, in case the master is not able to fulfill a request, the master will store the request in this queue and will use this queue later on, and it will also use a flag to indicate whether the CS is full or empty. Now, this indication is only for the master's machine and is not visible to the outside world. So, the master physically has to send a message to indicate whether a process is allowed to enter or not. And also we use a special message called a go ahead message to tell the process, yes, you can enter the CS. So, what are the actions of a participating process in the group? It can enter the CS. To enter the CS, it has to send a request message to the master and then wait for the go ahead message to come. When the go ahead message comes, it will enter the CS, it will execute the CS. At the end of the execution of the CS, it will execute an exit function, which is only send an exit or a release message to the master. So, a process, when it wants to enter, it will execute an enter function, and when it is done with the critical section, it will send an exit function. The master, on the other hand, will be waiting for a message to be received, a request message to be received. When it receives a message from, say, some process Pi, it will look at the flag to see whether the CS is full or empty. If the flag says that CS is empty, it will simply send a go ahead message, GA message to the process requesting process Pi. If the flag says it is full, then it will put the value of that Pi into the queue. And when it receives an exit message from a process, which means that already master had sent a go ahead message and the process was in critical section, it completed it and then it is sending an exit message. Then what it will do is, it will take from the queue one of the processes which is waiting and it will send a message to that process go ahead. Right. So, if there are no processes waiting in the waiting queue, then it does nothing on receiving an exit message. Let us look at an example. Here are 4 processes P1, P2, P3 and P4, and we have a master which is maintaining a queue and it is maintaining the flag. Initially there is no process in the CS, so therefore CS is empty. Now assume that a request comes from P1 and master looks at the CS and sees that the flag is empty. So, it sends a GA message or a go ahead message to P1 and makes the CS, indicates that the CS is full. Then during this time another request from P3 comes, the master checks the flag and sees that the flag is CS is full. It puts the number of this process into the waiting queue. Then another request comes from P2, again the flag says the CS is full. So, P2 is put into the requesting queue, waiting queue, and P4 sending a message also gets entered into the queue. Now, when P1 sends an exit message indicating that its job in the CS is done, it makes the flag as CS empty, looks at the queue, finds that P3 is waiting. So, it takes P3, it will send a go ahead message to P3 and it will indicate that the flag is CS is full. And similarly, at the end of this, P3 will eventually send an exit message and P2 will be removed and then P4 will be removed and so on. So, this is how a centralized solution can maintain a mutually exclusive critical section. So, now looking at the analysis of a centralized solution, we see that there is safety. This safety says that at most one process will enter the CS, and since it is controlled by the coordinator, we can easily ensure that one process alone enters the CS, and the liveness says that no process should wait forever because there are only n processes. So, there will be n entries in the waiting queue, and n being a finite number, liveness is also guaranteed. FIFO ordering of the request can be unfortunately guaranteed only when in the order in which the coordinator or the master receives the requests. Now, we are ready to look at another example, which is called a token ring algorithm. Now, token ring has n processes and these processes are connected in a virtual ring. We know already that a virtual ring is not a real ring, there is no physical connectivity involved, but a process knows to which process it should send the message, and it also knows from which process it will receive a message. So, therefore, this is called a virtual ring, and we use a token. Now, what is a token? A token is nothing but a message, a special message. This message will be passed along the ring and it will be received by a process, and the process's interpretation for that message is what makes this a special message. So, let us look at the algorithm. The algorithm has three functions. One is called the receive token, the second is called the CS entry, and the third is called the CS exit. On receiving token, if a process receives a token, it will enter the CS, execute CS entry if it is interested, otherwise it will simply pass the token. Now, in CS entry, if a process is interested in, say this process is interested in entering the CS, it will wait till the token arrives to this process, and when the token has arrived, it will hold the token, it will not let the token pass, and it will execute the critical section. And on completion of the work in the critical section, it will execute a CS exit, in which case it will simply pass the token to the rest of the next process and so on. So, therefore, then the token will again do its round around the ring, and when it comes to the again another CS entry, it will stop. So, let us look at the correctness of or analysis of this token ring algorithm. Safety says that there should be only one process in the critical section. So, we have in a token ring algorithm, we are saying that there can be only one token. So, and entry in CS is guaranteed if and only if, or is allowed if and only if the process possesses the token. So, therefore, of course, no two processes, since there are only one token that is there in the environment. So, only one process can enter the CS at any point in time, thereby guaranteeing that safety is followed. In case of liveness, we have that assumption that no process fails with the token. So, therefore, the token will always be alive in the system, and whenever a process is completing, it will send the token along the ring. So, a process within a finite time, if it is waiting, it will receive the token, and as soon as it receives the token, it can easily continue in the critical section, it can enter the critical section. So, a process is waiting for the token to come. Whenever the token comes, it will enter the critical section executing a CS entry. So, this is how our environment works, and let us now look at who uses mutual exclusion in a cloud environment. Chubby is a Google system mechanism, is a tool actually which is extensively used by various processes for locking mechanism, and Chubby has locking mechanism which is extensively used by different other Google's tools. It is used by Bigtable, it is used by Megastore, and many other mechanisms in cloud use Chubby as their locking mechanism, and Chubby provides what is called an advisory lock. Unfortunately, it does give mutual exclusion, but the mutual exclusion guarantee is not provided. It only assumes that if all the processes involved in the mechanism are willingly executing the locking mechanism, then it will be mutually exclusive. So, it leaves a lot of processes to execute on their own, and if a process defies tries to defy or wants to defy the locking mechanism or the mutual exclusion, the process can do so according to how Google implements it. So, the Chubby maintains a group of servers and elects one master. They use one of the election mechanisms to elect a master. When any client, that those are the participating clients accessing the cloud, if a client is looking for access to a mutually exclusive code, then what it has to do is it has to ask the master. If it is only reading, then it asks the master, and the master is one of the data servers having the shared data. It simply allows the reading from its own data. If it is a write request to the master, then the master does not allow a write easily. What it does is it asks all the other servers where the data is replicated, all the other servers it will ask, and what it obtains is called a quorum or a majority. So, what is a quorum? Quorum is a mechanism in which normally we see this being implemented in a meeting, where we say in a normal meeting where we say that minimum percentage of people have to be present for the meeting to be held. A quorum is called a quorum. So, here in Google's Chubby, and in fact many other mechanisms where we use the mechanism of quorum, they use it this way, that they predefine a number, a minimum number who have to agree for a certain work to be done. So, what here Chubby does is Chubby sends requests that this write is requested, is it okay for you to allow this write, and each of the participating servers will respond. Now, in case the current write will violate whatever has been written earlier on, or some other write that is going on in one of the servers, that server sends an objection saying that no, I am not ready to accept this present write. Similarly, all other servers will respond, and what Chubby does is, in case the number of responses are in accordance to the quorum number that they have predefined, then it goes ahead and writes the value. So, that means that in case the quorum is maintained, that means majority of the servers are are okay with the current update, then Chubby goes ahead and commits the value. And accordingly, whether the write can be done or not. In case the quorum number is not agreeing to accept the write, then it says no, sorry to the client, that at this point in time the write cannot be done. In case the response is okay from a minimum quorum number, then it writes and sends the response saying that yes, write is done. Similarly, in case there is a failure of the master, then it simply executes the election process and selects another master from among the servers, and the process continues. A similar mechanism is also available in Apache Zookeeper. Zookeeper is another tool extensively used in the cloud environment, and Zookeeper also has a similar mechanism for mutual exclusion. Now, here in our two algorithms, besides these two algorithms which we have discussed, there are other algorithms which are purely distributed algorithm. The problem of centralized algorithm is like we discussed in Chubby. The problem of centralized algorithm is that the master may fail at any point in time. If the master fails, then we get into the problem of electing another master, and till such time as the master is not elected, we cannot continue with the rest of the work. So, that is a big problem for centralized solution, and in a token based solution, the problem is that in case there is a failure of the token, then we cannot do anything. We have to wait for a token to be recreated, and only then the work can continue. So, these are the typical problems of these two environments. A distributed environment, distributed algorithm can be implemented and can be executed. So, here is the summary of today's lecture. Today we saw why mutual exclusion is required in a distributed environment, and hence therefore, it is equivalently required in cloud. We looked at two classical mutual exclusion algorithms. They are one is called the leader based algorithm or a centralized algorithm, and the second one is the ring based algorithm, which is a token ring algorithm. And then we looked at how these algorithms or similar algorithms are implemented in cloud. So, in the next class we are going to look at the snapshot system. These are the references. Thank you.